Hello, welcome to SCP-140's discussion of the fourth problem set in the class. I'm going to walk you through some of the problems and hopefully give you some hints for how you might solve them. Here we are on our Blackboard site, and we're up through week 8, fourth problem set, outer solar system and stars. If I click on this problem set, I'm going to be able to go through here and look at what I'm asking you to do this week. There's some resources available, and the questions should be coming of the type that are more familiar to you. The first question deals with moons in our solar system. You should be able to find information about all of these moons in your text, so please do look through those. Question number 2 asks you to think about a property that stars have called luminosity. If you look up the luminosity of stars in the appendix of our text, which is linked here, you'll be able to figure out how many light bulbs you would need to approximate this star. To do this, you need to write a number in scientific notation. So let me show you how you do that using your keyboard. Let's say I wanted to write a number like 5 times 10 to the 20. So to do that, I could write 5. And then the thing that confuses many students is they want to write the letter X for times. Now that doesn't really work here because this system often thinks that the letter X stands for a variable and not for multiplication. So if you want multiplication, what you use is the asterisk, which is Shift 8 on most keyboards, and you'll get a little dot like this. Now I'm not done yet, so I need to continue writing, but I will here. I'm going to write 5 times 10 to the 20, and to write to the 20, I can either press this button here, which is X with a little box up in the superscript, like this, or I could have typed Shift 6, which is a little caret, and it would do the same thing. Then I write the number 20 like this. That's complete syntax. That's in scientific notation. Now, I'm not saying that this is the right answer. You're going to have to calculate that for yourself, but this is the format that you can use to enter that answer. You can also look at this question here, where you might think that a different object might appear brighter at different locations. So in this situation here, we're looking at another location, Pluto, 33.5 AU from Earth. And we're trying to ask, well, how much brighter would this star look if we moved it to Pluto, right, where Pluto is located? So it starts off at a distance of 4.2 light years and then moves to a distance of 33.5 AU. It's much, much, much closer. That means it's going to be much, much, much brighter. In order to solve this problem, you're going to have to recall something about luminosity and the way light behaves as you move further away or closer. And that is, it follows something called the inverse square law. Let's say I move twice as far away from a light source. That means the light source is going to be 4 times dimmer, because it's not only half as dim, it's 4 times as dim, because 2 squared is 4. I have to square the distance to know what factor to multiply or divide by to figure out how the brightness is changing. So I have 4.2 light years here and 33.5 AU. I can divide those two distances by each other, making sure that they talk to each other in the correct way. They need to be in the same units, the same distance units to compare them. And once I do that, then I'll have a factor of the difference in the distance, a multiplying factor or a dividing factor. The brightness then will be related to the square of that number, and that's what I'll be looking for here. And this is mentioned down here below. You can use some of these pieces of information to help you answer this question. It's a very good question for making you think about how things will change in brightness. As I move to different locations, farther or closer, how will things look differently in the night sky? Question number 3 asks you to measure the temperature of certain stars by looking at their color. So the first thing that you're going to do is notice that this star has a particular color, and there's a scale of temperature you can compare it to. Once you submit that temperature, you're going to be asked some questions about what it would be like to live in a solar system that had a star of that color. Now, this particular color that I'm looking at happens to be a color that will be a little bit colder than our sun. You might get a color that's a little bit warmer than our sun. If you get a color that's warmer than our sun, you would expect the Earth's temperature to be warmer. Let's say the star's temperature was twice that of the sun's, measured in Kelvin. Then you might expect the Earth's temperature to be twice what it is. This is assuming that the star doesn't change in size. That's a pretty bad assumption, but it's one that'll help us make the calculations easier. So that's what we'll be doing here. In this situation, my star is colder. So I'm going to expect to see a colder temperature on Earth. How much colder? Well, I'll take the temperature I figured out for this star, and I will divide it by the temperature of the sun. That factor should be the difference of the temperature on Earth, and it'll tell me what the average temperature on Earth is. It's roughly room temperature or so, maybe a little bit colder. So we might think of it as being about 285, 290 Kelvin, which is about the way we would measure that in degrees Kelvin. Then I would multiply that number by the factor of the ratio of the two temperatures, and that would give me a new temperature for my planet. Would it be too cold for life to live? Too hot for life to live? Different people have different answers depending on the color of their star. That's for you to look through and for you to make some investigations of. Question number 4 asks you to look up some interesting properties about stars that have planets around them. Here's a number of different stars. And as you look up these planets, which are the little letters that come after the name of the star, you're going to find that each of these stars has something called a spectral type. This spectral type is going to become more important as we investigate further and further along in this class. But this is just something to get you used to looking up spectral types and thinking about them. The spectral types in order are letters that were first assigned back when they didn't really know what they were doing and they were looking at spectra. You can look at the video that I posted about stars to learn more about that. But eventually they found that these letters were ordered in order of temperature, which meant that the hottest temperature stars had a spectral type of O, and the coldest temperature stars ended up having a spectral type of M. And the order of the letters from hottest to coldest was O, B, A, F, G, K, M. Sometimes we teach students to memorize these. That's not so important. You can look them up and see what these different spectral types mean. Often these spectral types will have numbers behind them. That just says how far along they are in the temperature sequence. A smaller number means it's hotter, and a larger number means it's colder. So, for example, you can see here there's a spectral type of K1. That's nearly a G-type star, OBAFGK. So something like K1, if it was a little bit hotter, it would be more like a G9 star. Here we see there's a G8 star. If it was a little bit colder, it would be a G9 or a K1 star. Now, question number 5 is one of the more difficult questions we ask you in this class. It's asking you to consider a diagram called the Hertzsprung-Russell, or HR diagram. This diagram contains a tremendous amount of information on it, and we should spend some time thinking about what this information is. First of all, this diagram, as described in the discussion that we had in the text and also in the videos that you're watching, includes every single star that can be observed. But the stars are not arranged as you see them on the sky. They're not stars that are close on the HR diagram are not necessarily close in space. You wouldn't see them next to each other. Instead, we're looking at different characteristics. And the two characteristics we're looking at is how much light the star is giving off and what temperature the star is. Along the bottom, on what we would call the x-axis, you can see the letters that I was mentioning before, O, B, A, F, G, K, M, and also the colors that we'd already examined, going from the bluest stars, which are the hottest, to the reddest stars, which are the coldest. Now, even the coldest stars are much hotter than any temperature you would ever be able to experience. You can see the temperatures go down to 3,000, maybe a little bit lower, to 2,000 Kelvin. 2,000 Kelvin is the temperature of a really hot oven, but it's a very cold temperature for stars. Meanwhile, the hottest temperature for stars are in excess of 30,000 Kelvin, which is very, very hot. And you can see that range down there. On the y-axis, the vertical axis going up and down, you can see different measurements for the luminosity of stars. And the range is absolutely enormous. This range is going up by factors of 10 for every tick mark. So right in the middle, you see a range of 1. That's the same as the luminosity of our sun. Our sun gives off 1 solar luminosity. But if you go down from there, you can see we go all the way to 10 to the minus 5, which is 100,000th the amount of light the sun gives off. A much more dim star than our sun. Imagine if we had a sun that was 100,000 times dimmer than ours, shining light. It would be a very dark day, even at noon, if that was the star we would have shining light upon us. You can also go the other direction. You can see well above on the vertical axis, it goes all the way to 10 to the 6 and higher. That's 1,000,000 times much more light than our own sun gives off. Now, if you arrange all the stars you observe in the sky, you'll see that they clump or come into patterns. And the biggest pattern of all is a sequence of stars that goes from the upper left-hand corner of the diagram all the way down to the lower right-hand corner of the diagram in something you'll see as the main sequence. 90% of stars lie on that main sequence, including our own sun, which has a luminosity of 1 solar luminosity and a temperature around 6,000 Kelvin. You can see the sun on that diagram, and also lots of other stars as well. This main sequence, it turns out, is a sequence of stars that are ordered in terms of mass. These are stars that are burning hydrogen at their core. And if you have a star that's a certain mass that's burning hydrogen at their core, that actually determines almost everything you can possibly know about this star. It determines how much light it's giving off. It determines what temperature it is at its surface. It determines its size in radius. In other words, how much space it takes up. And it also determines something very interesting: how long that star is going to continue to shine in that fashion. We call that the lifetime of the star. And you can see the lifetimes indicated on this diagram with green bars. The shortest lifetimes are up at the top at 10 million years. Sounds like a short amount of time for astronomers, long amount of time for human beings. But that's actually very short if you think about the entire history of our universe. The longest lifetimes you see on here go down to 10 to the 11, and there are some stars on here that probably will live 10 to the 12, which is 1 trillion years, much longer than the universe itself has been in existence. These stars are much smaller, much colder than our own sun, but they don't use as much energy, and so they will continue to shine for much longer. Whereas the stars that do not last as long, those are much larger stars, much brighter stars, much hotter stars. We say that the big stars, they burn through their fuel very quickly. They're burning up really fast. They're dying young. Whereas the smaller stars, the colder stars, they can live much longer, burning at a much lower rate. Our own sun will last about 10 to the 10 years. And if you look at how old our sun is from the observations that we've been seeing in the text, you'll know that our sun has already gone through about 4.5 billion years or so. So we have about 5.5 billion years left for the lifetime of our sun before something happens and it changes its characteristics. When a star in the main sequence does run out of its fuel, it ends up going into another phase of its life, which we'll discuss in a future exploration of what we call stellar evolution in about a week or two. In short, these stars end up becoming very large, and they also cool down a little bit. As stars get larger and cool down, they will give off more light, but they'll end up being redder and redder. So we call these things red giants. There are other stars that are similar temperatures, but are much smaller. We call red dwarfs. Those tend to be on the main sequence of our diagram, as you can see here. Then there are stars that are much bigger than our own sun, but happen to be very hot on the main sequence. We call those blue giants, sometimes even blue supergiants. And there are supergiants, which are much bigger than the giants seen on this diagram as well. There's a relationship between giants and supergiants, but you'll get a chance to investigate that later. Finally, after the supergiants and the giants use up all of their fuel, their outer layers end up dissipating away, and what's left is a tiny hot core that's much, much dimmer than a normal star, but a little bit hotter. Those are the so-called white dwarfs you see in the bottom right of the diagram. There's 2 stars indicated there. One fun thing that is on this diagram are some diagonal lines that tell you how much space stars are taking up. We say that the way to measure these stars is in terms of their radius, the distance from the center to the outside. One solar radius is about how large our sun is, 700,000 kilometers. But there are other solar radii indicated on the plot as well, and you may be asked some questions for how to figure out different stars and how big they are. Additionally, you can see the sequence of mass along the main sequence of stars, starting at the very top where we have a star that's 60 times the mass of the sun, going all the way down to the bottom, a star that's 1/10 the mass of the sun. Now, down here, you're going to see a number of different measurements, masses, sizes, spectral types, temperatures. You'll see different names for different kinds of stars. All of these things are discussed and described within our text in the video, and even some of the things I just shared with you right now. To figure out what each of these stars are, what you're going to have to do is look very carefully at the diagram to see where it might lie. Where is spectral type B? Where would I find red dwarf stars? What would I need to do to figure out how luminous a star was? Those are different things you're going to answer in different ways using the above diagram. I'll give you a hint. Only one star is used for each of these questions. So if you click on here, you'll see a lot of different stars named. If you find one star that you think is correct, and then later on you think that the same star should go there, you know one of those is wrong. The goal here is for you to do the matching as well as you can before submitting. It may take you a while to go through and figure out where all these stars are. But as you work through this, my hope is that you'll come to a better understanding of this very important diagram. Some people consider this one of the most important diagrams we've come up with so far in astronomy, because it really gives us a sense for how stars behave. And we'll actually be able to make predictions based just on this diagram of what the future might hold. Of systems might exist out there in the world and in the universe, and how stars really define the environment of space as we know it. The remainder of questions on this problem set are multiple choice questions that are tied to the chapters that you're reading and also the videos that you're watching. So I hope that you'll go through here and be able to find the answers as you go and investigate these. But that's problem set number 4. There's one very difficult problem on this problem set. I would say that's problem number 5. You're going to need to spend some time working on this to get a good score on it. But I'm hopeful that you will learn enough to be able to answer it well and get some interesting insight into the nature of stars by doing that. So thank you very much. And we will continue to discuss these matters and explore more things as we go on. Have a wonderful rest of your day, and I will talk to you very soon.